Okay, so let's try and do an example where we can actually see the power of using this idea of a material derivative, particularly for something associated with acceleration. And there's a couple of problems that we'll make available. One is thinking about a rocket accelerating, and there's a separate file for you to look at for that. And the second one that's also talked about in detail is the idea of rigid body acceleration, which is something that you've probably all seen as an undergraduate in physics. The idea that if I swing something about my head, as I do that, even if I do it at steady velocity, there is the idea of an acceleration, and you've called this probably in the past centripetal acceleration. So this must be something that should be described by this idea of a material derivative. In particular, we can see that a Lagrangian description would be to say that if I think about a material point, as labeled here, x, this might be moving in a circle about a center here at a rate omega, and we might well think that the magnitude of the velocity we know is a constant, and the magnitude of the velocity is set by the distance away from the origin I am and the speed at which I'm rotating. So the magnitude of this would be r times the speed, which would be omega. But as I change position, even if I do this at fixed speed, so if I do this at fixed speed, I've definitely changed when I get here, because my velocity vector, which was pointing in this direction, is now going to be pointing down in this direction. So in terms of a velocity vector, there has been a change in the velocity, even though the speed has remained constant. And so if there's a change in velocity, there's an acceleration. And we'd like to be able to understand that. And probably everybody knows the result already, but we want to see how this is connected to the idea of a material derivative. So there's two different ways that we might describe these things. We can describe this in Cartesian coordinates, like x, y, and z out of the board, or we might describe it in terms of polar coordinates. And so we'll write down also the result in terms of polar coordinates. And the first thing for us to remember, of course, is that the distance x here is given in terms of r and theta as r cos theta, and y is given as r times theta. So if we were to write the velocity vector in polar coordinates, and it had these three components, vr, v theta, and vz, then we know that in polar coordinates, the velocity in the r direction is 0. In the theta direction, it's just r omega, and in vz, it's also 0. So that's our velocity, and it's constant. But what we really care about is we really want to evaluate the acceleration. And so that's what we need this idea of the material derivative operator to do. So we'll remember that this should be able to be found by thinking about dv by dt. Well, in this case, that's 0, but the term that we are interested in is this quantity v dotted into the gradient, and then operating on the vector v. So we're going to have to do that, and we can do that either in polar coordinates, or we can do this in Cartesian coordinates as well. So let's first of all think about what the velocity is if we write this down in Cartesian coordinates. So we would certainly, as I've drawn here, we can think about Vx being connected to this. So I might write Vx is equal to minus v theta times sine theta. And Vy is given as v theta times the cosine of theta. And to check our signs, we can always just think about what happens if we evaluate theta at, say, 0. If I do that at 0, and I've defined it as rotating in this direction, then the component of velocity is purely positive. And so at theta is 0, Vy would be equal to v theta times cosine of 0. If I get to 90 degrees, the velocity will be heading in this direction, which is, if this is my positive x, it will be negative, and so then Vx would be minus v theta times the sine of the angle, and when we get to 90 degrees, this would be the sine of 90, which is 1, and so the velocity will be in that direction. We can combine that with this idea that the v theta is r times omega, so we could also write this in terms of r omega sine theta, and this as r omega cosine theta. And then we'll recognize that if we do that, we can combine that with these statements as well. So we can also write this, and of course we need a minus sign there. So we can also write this as Vx is being equal to r sine theta. That gives me a y. So this gives me minus omega times y. And this one, r times cos theta, is x. And so this is just omega times x. So now we've got expressions for Vx and Vy in terms of the current positions. And now this is something that we can now use by combining it with this idea of the material derivative. So what we're going to need to do is we want to evaluate V dotted into the gradient of V. As we do that, we will write this in terms of two components. We'll have Vx d by dx plus Vy d by dy. That's the V dot gradient operator. And then that's going to be operating on this quantity, which is our velocity. So this whole quantity has to operate on both Vx, Ex, and on Vy, Ey. And so we're going to have to think about differentiating both of these quantities this way. So what are we going to get when we do that? Well, we can see what we're going to get when we put this in here. If we just evaluate the Vx component to start with, we'll put this in here. And then Vx looks like it depends on y, and so we'll have to think about Vx times d by dx. Well, there is no x dependence of this, so this term will actually certainly turn out to be 0. So this first term will turn out to be 0. But what we're going to end up with is a product that looks like Vy times d by dy of Vx, and Vx is minus omega times y. And that's going to have a base vector associated with it, which is Ex. Similarly, for this one, we're going to have to think about derivatives with respect to x and y of Vy. Vy looks like it's omega times x, and so if I put that in there, there's going to be no dependence from this term. There is going to be this term, so we will end up with, in this term, Vx d by dx of Vy, and Vy is omega times x. And that's going to have a remaining base vector Ey associated with it. So we can evaluate these two terms. And we're going to get minus omega out of this, multiplied by a Vy. Vy is given by this, omega x. So we're going to get minus omega squared times x times Ex. Here we're going to get a Vx. A Vx is an omega y. D by d this of this is going to give me an omega. So we'll get also a minus omega squared y times Ey. And so our centripetal acceleration looks like it's inwardly directed. Both of the terms are negative, so they're inward directed, and they depend on the positions and in this way. So this is our acceleration. And the final thing that we might like to do is we might like to express this back in terms of coordinates that are polar coordinates. And so we can also substitute in here that this would look like r cos theta, and we can also substitute in here that this looks like r sine theta. And finally, if we want to convert this into polar coordinates, then we can easily do that as well by using the identities that we've got down here. And so when we do that, we'll end up finding that in polar coordinates, so this is it in Cartesian coordinates, and in polar coordinates, as we show you in the handout, by combining x squared plus y squared is equal to r squared, we'll find that the acceleration is equal to, in polar coordinates, is equal to minus omega squared times r in the minus er direction. So a result that you're probably all familiar with from physics is that there is an acceleration. The acceleration that we experience here is in this direction, and it's of magnitude minus omega squared times r. If we combine that with this statement that the velocity is given by this, you might also have seen it written as v theta squared over r times ER. And it comes naturally from this idea of the advective term, that even if my flow is steady, by changing position, I have changed acceleration. And that's the power of using this idea of the material derivative.